Alright, so this next video is about the drinking and driving example. As you could see here, here's this nice happy face before, right? And then they drink 2 beers. And then after, what are they like as a driver? Now, one hypothesis is, from some college students is, hey, 2 beers is nothing. I'm basically the same person that I was before and after. I could drive equally well, right? But other people are like, I don't know if I'm the same before I drink 2 beers and after I drink 2 beers. Maybe I'm really different in my driving ability. So here we have all the data from the 20 students who participated in this study. And here, so each student is on one row, right? And you see their before they drank braking times, right, in seconds, and their after they drank braking times, right? And in this case, faster braking, so a lower number of seconds, is a good thing, right? Because you want to hit the brakes as soon as the obstacle appears in the road so that hopefully you'll brake in time, right? So, if you look at this guy, this person right here, this person, 6 seconds, pretty slow, right? But then there's a really fast person here who has like 3 seconds, right? And so that person's faster, right? But this is all before they drink, right? This is them sober. Now, after they drink, some people get sort of faster, some people get sort of slower, right? So if you look at this really fast guy, he got slower, right? So he went from about 3 seconds to 4.5 seconds, right? So he got slower at braking. He got worse at braking, right? But if you look at somebody else, like for instance, this guy was 5.19 seconds, they get faster after they drink beer, right? A whole second faster, right? And so, some people get faster, some people get slower. And the question is, well, are they different before and after they drink a beer, or are they really the same person? Can college students sort of get away with saying, 2 beers, I'm not affected by that. I'm not a different kind of driver. I'm the same kind of driver, right? Can they say that? Well, one thing we would like to see is, well, what are they like before and after? Because some people are generally sort of fast, right? And some people are generally sort of slow. So we want to know, well, here's their before score. How much faster did they get, right? And so here's how much faster they got before minus after. So if you look at, look at this guy. Oh, I keep touching it. Oh, let's look at this guy. 5.19, and then after they drink 4.19, they got a whole second faster, right? And so, wow, that's pretty impressive, right? But then this other guy, I don't know if they're all guys or girls, but I'm just saying guy for now. This other person was 4.85, but then they got slower, 5.91, right? So they got like a second slower. So here, before minus after will give you how much faster they got. This one gets a -1 because they didn't get 1 second faster. Negative means the opposite. So they got 1 second slower. Now, statistics is the math of distributions, right? And even if drinking had no effect, maybe we just made them drink water or something, they might be a little bit different after they drank the water than before they drank the water, right? Maybe you braked at 6.2 seconds before, but 6.3 seconds after, right? But on average, it should even out to no difference in how good of a braker you are. And if anything, you should get better, you should get faster because you've had practice, right? You've already done it once, you should be a little bit better the second time around, right? And so here, what we want to do is we want to see, well, are they different before and after, or are they the same before and after, right? And so that's what we're really going to try to figure out here. So in this distributions triad, we have this sample of 20 students. Now, obviously, they are not every single student who has ever drank 2 beers in the world and driven before and after, right? It's just a sample, right? But we really want to know about the general population. Like, does drinking affect the general population? Unfortunately, we cannot just go from the sample and make some sort of conclusion about the population because, after all, samples are all slightly different from their populations. So that's why we're going to have to bring the SDOM into all this. So let's get started on our hypothesis testing. So this situation is a situation that the book calls a matched pair design. It's also called a paired samples design because the sample of people before are the same people who are sampled after they drink 2 beers, and so their before scores have a little partner. They have a pair in the after scores, right? And what we're really interested in is, hey, are these before scores the same as the after scores or not, right? And one easy way to do this is to say, well, what's the average difference between these 2 scores, right? If there's no difference, then the average difference should be 0, right? And so that's going to be our null hypothesis, that the average difference is 0, right? So I'm going to write that here. That the mu, in this case, the mu stands for average difference is 0, right? Or maybe there is some effect. Maybe alcohol makes you slower. Maybe alcohol makes you faster. Who knows? It did for that one person, right? And so maybe mu is not equal to 0, right? So here let's think about what this null hypothesis means. What is this? You see this little drawing of the circle here? What is the pool that we're randomly sampling from? Well, we're randomly sampling from a bunch of differences, right? Some of these differences are positive because they're getting faster, and some of these differences are negative because these drivers are getting slower. All right, so at this point, let's return to our distribution triad, right? So what we really want to know about is the population of all people. How do people in general act after they've had 2 beers? Are they faster or slower at braking? Are they different at all, right? That's what we really want to know. But we can't drag the entire population of the world into a lab, force them to drink 2 beers, and make them do a driving simulator before and after. But we could ask 20 college students to do that, and that's apparently what they did here. And so they had 20 college students do this. And here the mean difference here was negative 0.46 seconds. So on average, they got slower by 0.46 seconds. Not quite half a second, but about half a second, right? They're like half a second slower, right? And the standard deviation is apparently 0.87 seconds, right? All right. Now we want to know, well, is this sample likely to have come from a population where the actual mean difference is 0, right? And I'm going to put a big question mark here because I don't know, right? Maybe they're not that different. Half a second. Maybe that's not really that different, right? Well, it'd be nice if we could just directly go from our sample to our population and say, oh, yes, this means that this is not the population, right? But we can't do that because you know what? Samples are all slightly different from each other, and maybe if we got another sample, that sample would be faster by half a second. Then on average in the population, it really is 0 difference, right? So what should we do? How do we know whether the sample is likely to have come from this population or not? Well, one thing we could do is we could draw all the possible random samples from this population, right? We could do that. And we don't need simulations to do it because we could use the CLT. And then what we could do is compare this sample to all those random samples drawn from that population. So we could compare them. And and actually get a number of how likely is it that this sample came from this population. And then, through this process, be able to say something about that population. Is that a likely population given this sample or an unlikely population given this sample? So here I'm returning to my steps of hypothesis testing. Notice that my steps of hypothesis testing don't necessarily correspond to the book's steps of hypothesis testing. But both of them have all the steps in them. It's just that, we want to make it orderly for you. For me, I'm going to stick with mine. All right. So here, step 2 in the steps of hypothesis testing is setting your alpha. And here, as usual, we set the alpha to 5%. So what does this 5% mean? It means that if this sample is less than the likelihood that this sample was randomly drawn, remember my hand motion, randomly drawn, if the likelihood that this sample was randomly drawn from this population of no differences is less than 5%, then I'm going to say this is probably not how we drew this sample. This is probably not the population that this came from. Now, if I drew all the possible random samples from that population, what kind of sampling distribution of the mean would I get? What kind of estimate would I get? Well, the book takes care to point out that here we have sort of a small sample size, n equals 20. So in this case, we're not really sure that this is a t distribution. We are not sure if it's a t-shaped. But one of the little tricks you could use is that if sample size tends to be small, and you look at the sample and it's not too badly skewed to the right or to the left, then the t distribution is still a pretty good shape for that sampling distribution. So I'm going to draw a t distribution. I wrote that this is an estimate and that it's t-shaped, right? And from the CLT, we know that the mean of this estimate is the same as the mean of the population that it was drawn from, right? And through the CLT, we could estimate how big the standard error of this thing is. And we could estimate the standard error using S, which is 0.87 divided by square root of 20, right? S divided by the square root of n. All right, and the number for that is 0.195. So that's how big the smoot is, right? All right, so here we've set up our sampling distribution of the mean. And now we want to know, where does our sample fall on this, right? So we know that the sample mean is about half a second slower. So on average, our college students, the 20 college students in our sample, are about half a second slower, negative 0.46, right? And we want to know, where is negative 0.46 on this estimate, and what's the likelihood of it? Well, if the size of that smoot, or standard error, is 0.195, right? How many of those can lie down in between 0 and negative 0.46? It looks like maybe 2, a little more than 2, right? But you could be exact by using our t-score formula. And here it's a sample t, because it's telling you the distance of our sample away from the mean. So negative 0.46 minus 0, which is, just negative 0.46, all divided by the size of our smoot, which is 0.195. And when you actually calculate that out, it's negative 2.36. So negative 2.36. And so I'll sort of draw what that means out for you. So about 2 and about 1/3 of a jump away, right? So here's a standard error, and it's 0.195. Here's a standard error, and it's 0.195. And here's a little bit more. It's 1/3 of that 0.95. And here it's negative 0.46. Our sample is right there. Okay? Now, is that sample pretty far away from the mean? Well, just eyeballing it, it looks pretty far away, right? And when you use SPSS or something, what you see is that the p-value here, right, is 0.015. So here, the p-value, so that's that area, the probability, that area, the p equals 0.015. Okay. Now, this is just a one-tailed p. And so in SPSS, it's going to give you a two-tailed p. And that's going to give you, that's just going to multiply that by 2 and give you a p-value of 0.03, right? So let's think about what that p-value means. So here, also add this point. And so if you add those two sides, those two tails together, you get 0.03. And so our two-tailed significance level, or two-tailed p-value, is going to be 0.03. I know the book does one-tailed, but you should do two-tailed. So what does this p-value mean? It means, so I'm going to write the p equals 0.03 somewhere. So this p-value, let's think about what this means. There's a 3% chance of getting a sample statistic this extreme. 2.36 standard errors out, right? That's far away in t-distribution terms, right? There's only a 3% chance of getting that extreme of a sample if this sample was randomly drawn from a population that had no differences. So that's pretty low probability. That's lower than 5%, which we used as our alpha, right? And so in this case, we would reject the null again, right? So I don't have room to write reject the null here, but know that we reject the null here. All right, so here I want to draw alpha so you could see. And alpha, I'm going to draw in red. So alpha would be something like this. And alpha on this side would be 0.025. And this alpha on this side, 0.025, right? And alpha is also two-tailed because we're always doing two-tailed tests. And so when you add those alphas together, you get 0.05. Just like when you add those two sides of the p-values together, you get 0.03, right? Now, SPSS is just going to do the adding for you already and just go straight to the two-tailed p-value. So just know that when you're doing SPSS. And that's why it always tells you significance, two-tailed, All right. So here we return to our original question. We really want to know, does drinking 2 beers make any difference, at least in your breaking skills? And at least from our sample, we're going to reject the idea that drinking 2 beers does not make a difference. We think that it does make some difference. And so let's go back to our distribution triad. Here, what we saw was that when we compared the sample to all the other samples that we could have randomly drawn from this population of no differences, right, that this sample is pretty unlikely. Oh, I should draw these in green. Sorry, I didn't do my special color coding, right? Just circle it in green, right? Because those are our sample. So our sample is pretty unlikely given this null hypothesis, right? And so we use this to say, given that this was our sample, we don't really think that was the population. We don't really think that the truth is that drinking 2 beers does not make a difference. We think it probably makes a difference.